Hello. In this video, we will look at the chain rule for multivariable functions. To start, let's review the chain rule. So the chain rule in Calculus 1 is used to go through and calculate the derivative when there's a composition of functions. The multivariable version could be used for the same purpose, but is typically only used in proofs. So a couple comments on that. Why only for proofs? Because as I will show at the end of the video, it isn't necessary. If you're going through and you're calculating a chain rule derivative used in the multivariable situation, you can go through and you can just substitute and then differentiate. And so you can work your way around it using the Calc 1 definition. Now, the consequence of the fact that the multivariable version is only used for proofs is that this video is going to be a short video. I'm just going to give a fairly brief overview of how you go through and calculate a multivariable chain rule definition, and then we're going to conclude the video. So to start, going through that overview, what we're going to do is we're going to go over the Calc 1 chain rule again, but we're going to use what's called a derivative tree. All right, so the Calc 1 chain rule, the situation could be set up such that, so you have a suppose y equals f of x and x equals g of t. So you have to have two functions in the Calc 1 definition for a chain rule. It's a composition. It's when two functions are composed in each other. If you took the second definition and plugged it into the first, you'd end up with y equals f of g of t. And you can see it does have the same format. The only difference here is I'm just using t instead of x inside. X is being used as the middle function. But we could go through and represent the Calc 1 chain rule in this form, where you have a function definition and a second function definition, and then if you compose them, you do get the combination that we're accustomed to. Okay, so a derivative tree, what you're going to do is you're going to start off with the kind of the parent variable, if you want to think of it, the most dependent variable, and that's going to go at the top of the tree, and you're going to work your way down, going to independent variable to independent variable. So the independent variable in this function is the x, but then in this function, x is the dependent and t is the independent, and so you go from kind of the final variable, the most dependent variable, the end variable that your result's going to be in terms of, and then you work your way down the tree by representing, dependent variables in each case. So once you've got your tree written out, so y is based on x, x is based on t, it looks like this, then you're just going to calculate derivatives down the tree for each chain. All right, so you've got y versus x. If you took the derivative there, you would have, you differentiate y with respect to x, so we'd get dy dx. And then you have x is in terms of t, and so if you differentiate that, you'd get dx dt. Okay, and then the way that you can go through and calculate the final derivative, and the final derivative, I'm just going to draw a line from top to bottom to represent the final derivative. So the final derivative is dy dt. The way that you calculate it is by multiplying down the tree. So you'll get dy dt equals dy dx times dx dt. Okay, so let's recap that again. So we go through and we define the chain rule using these two functions, and you need to have two functions to define a chain rule because it's a composition of two functions. And then we can see that that's equals our original definition by just taking x equals g of t and plugging it in where the x is. And then once you go through and you want to create the derivative tree, that's what this is. What you're going to do is you're going to start with the final variable that your result's going to be in terms of, like if we plugged a number in for t, we would find x, and then we would take that x result and plug it in here, and then we would use that to find y. So our result's going to end up being in terms of y. So that's kind of the final variable, goes at the top. And then since y is based on x, you put a chain down to x. And then since x is based on t, you put a chain down to t. Once you've got this, you go through and you just differentiate down the tree. Y is in terms of x, so if you differentiate, you'd get dy dx. X is in terms of t, so if you differentiate, you get dx dt. And then from the top all the way to the very bottom, you'll have, your final result is going to be in terms of y differentiated with respect to t, so dy dt. And then to go through and write out the resulting result that you get from that, you take top all the way to bottom, right? So y is going to end up being in terms of t, so that's going to be the left side, and then it's equal to, and then you multiply down the chain to figure out how you'd get there. So it's going to be dy dx times dx dt. So that's what we get by using the derivative tree. Now, we're accustomed to going through and differentiating this. So we've long since memorized the chain rule. So dy dt, we could go through and calculate, and we know that that's going to be f prime of g of t times g prime of t, right? So this is what we get from just our memorization from Calc 1. Is this definition equivalent to that? So that's the question, right? So the left side clearly is, right? So we've still got dy dt over on the left side. On the left side of both, we have dy dt. What about these two? Well, what is dy dx? Okay, well, if you go and look at this, right? So if y is f of x, then dy dx, if you differentiate that, that would be f prime of x. Right, and then what is dx dt? Well, if you go to our x definition, if you differentiate that with respect to t, that would be g prime of t. And then finally, if you look at this, they may not look exactly the same. Well, that's because we have an x and a t, right? So our final result should all be in terms of t. If we take our x definition and plug it in, you get f prime of g of t times g prime of t. And so you can see based upon this example that the derivative tree method of going through and just going from top all the way to bottom to get the left side, and then to figure out the definition, we just multiply down the chain of all these individual derivatives, that does actually does work in the Calc 1 case. Okay, so clearly we could see that it does work in the Calc 1 case. All right, and so this is the derivative tree is going to introduce a technique that we can use when the tree is more complicated. So this is a very simple tree, but since the simple tree worked, in our Calc 1 case, we could try it in a more complicated case. So let's look at a more complicated case and what derivative tree we would get. And then we can go through and try and verify it in a way that's maybe a little bit similar to this Calc 1 case. All right, so let's suppose we had a multivariable function, z equals f of xy, and we had x equals x of t, and y equals y of t. Okay, and then so what would the tree look like? So we'd have to start at the top of the tree. We'd have z. Z is going to be our final result. And then we could work our way down. What is z in terms of? It's in terms of x and y. So we have two branches. And then x is in terms of t and y is in terms of t. So we have just one branch off of each. Okay. And then to go through and cut and figure out what these branches are going to be, we just take z, since z is in terms of x and y. If you were to differentiate that, you have to do partial derivatives. Can't do a regular derivative, so we're going to get partial of z with respect to x, partial of z with respect to y, and then down here we have dx dt, right? So you just do a regular derivative off of a single branch. X is just in terms of t, so that's a regular derivative. Y is just in terms of t, so that's also just a regular derivative. Okay. And now in terms of from top all the way to bottom, right? So the equivalent of, this last, kind of branch that I drew, if we went from top all the way to bottom, what would our definition look like? So with z is in terms of just t, so that's still going to be a regular derivative. It's still going to be dz dt. Okay. The way that you could think of this is that if you actually had functions here and you took these and you plugged them in, then you'd have z defined in terms of just a bunch of t stuff, right? Since x is in terms of t and y is in terms of t, you put both of those and plug them in, you'd have z just in terms of t. And so that's why we'd have a regular dz dt derivative from top all the way to bottom. Now, in terms of how, what the definition is going to end up being here. So as I said for the last example, you multiply down the chain. So if you multiply down the chain, we're going to have partial of z with respect to x times dx dt and partial of z with respect to y times dy dt. Now, this is the part that's going to seem a little strange, but what you end up doing with those two separate things is you end up adding them. So that ends up being our definition, is we multiply down the tree for both, and then we end up adding. So yes, the add is a little strange there, but that is the correct result. So I'm not going to go through and prove this in general. It's a much more complicated, more difficult proof. But what we can go through and do is we can go through and we can verify this in a simple case. And that verification will also, to some degree, justify the plus. So let's go through and look at showing this is true. So this is not a proof, it's more of a show. Show this is true in the case where we have z is f of x times g of y, and then x is equal to x of t, and y is equal to y of t. So now I have gone through and, these two are not the same thing. So our original supposition here is that z is defined in terms of x and y in any combination. They could be all mixed together. You could have, x's and y's together that are inside of other functions. It could just be quite complicated. So we're looking at a subset here where I'm saying that you've got X and Y, but you could separate them, right? So to give you an example, what could this look like? It would be like if we had X squared Y, or if you had cosine X times natural log Y. Or any other example that you could think of where the X's and Y's can be separated. If they can be separated, then we can go through. Then we can go through and represent them. In this case, with that structure. But yeah, I mean, you could have sine X, and you could have I don't know, cosine Y, whatever. Anyway, if you can get the two variables apart, then you can go through. So I can go through and we can go through and we can show that this is true as long as you can separate them. Showing that it's true if they're not separated, just in general, is much harder, much harder proof to go through and do. But this is actually a quite simple one. So let's say that we had this structure, and we wanted to go through and find the derivative of this. All right, so the way that you could do that is you could take these two things and plug them in, right? So we could have f of x of t times g of y of t. All right, now at this point, what you have is since x is defined in terms of t, that means x of t just has t's in it. So there's a bunch of t's inside of a function, and there's a bunch of t's inside of another function. If you're going to differentiate and you had a bunch of t's inside of a function times a bunch of t's inside of another function, you'd use the product rule. All right, so if we go through and calculate dz dt, to do that, we would go through and we'd say, all right, so we're going to have the first, which we just leave alone, times the, we're using the product rule, times the derivative of the second. So you'd have g prime of y of t. And so when we're differentiating the second, we can use our Calc 1 definition that we've just verified is true. So we'd have y prime of t. So you have the first times the derivative of the second. So first doesn't change, times the derivative of the second. And then plus the second, which doesn't change, times the derivative of the first. And if you use that to differentiate that, you'd use our Calc 1 chain rule to do that again. So you'd have f x of t times x prime of t. All right. Now, if you look at this, can we go through and translate this back into our original structure here? The easiest way to do that, I'd say, is probably in two steps. So first, you take x of t, that's equal to x. So we've got, this is f of x times g prime of y. Y prime would be dy dt. And then we've got g of y times f prime of x times dx dt. And if you look closely at this, right, so if we compare our original function for z and the setup that we have here after we've differentiated, compare those two. What's the difference between them? Well, we only differentiated the y. We left the x alone. If you only differentiate the y and you leave the x alone, right? If you differentiate the y but you leave the x as you treat the x as a constant, that's our notion of a partial derivative. That's the partial of z with respect to y. And then we have the same thing here, except now we've differentiated the x, but left the y alone. So that's the partial of z with respect to x. And you can see that is the definition that we said was the chain rule definition. So in this case, we were able to go through and show that the definition is correct as long as we can go through and separate the variables. So again, this does not show that the definition is correct if you can't separate the variables, but we're going to assume that it is. I'm not going to prove that. To go through and prove that, that's a harder proof. This is a nice, easy, simple, easy to understand proof that goes through and shows that the definition that we got from our derivative tree does work. And it goes through and it justifies the plus, right? So why did we end up with the plus in this case? All right, in this case, not in general, but in this case, we ended up with the plus because of the product rule, right? So that kind of makes it so that makes some kind of sense when you see that there's a plus between these. So you multiply down the chain, and then we end up adding them. Well, in this case, we add them because of the product rule, right? So if you go through and you differentiate a product, you end up with sum between the two. Okay, so that shows how to go through and find the derivative definition in this situation that is a composition of functions, right? This is a composition, just like our first case is a composition. You've got two functions. You take one, plug it into the other to create the composition. You know, we've got three functions technically, but we've got an outer function and we've got some inner functions. If you take the inner functions and plug them in, this is the kind of equivalent here of where we've got that composition where you've got functions plugged into other functions and you need to figure out what the derivative is. Okay, so this is the notion of a multivariable version of the chain rule. Let's look at another one. All right, so this definition is a bit more complicated. It's getting more complicated. So we have z, which is our final end result variable, is defined in terms of two variables, and each of those two variables is defined in terms of two more variables. So how would we go through and figure out what the formula for the derivative is in this case? You create a derivative tree. So we'll start off with z, and z is defined in terms of x, and z is defined in terms of y. And then x is defined in terms of u, and x is defined in terms of v. Y is defined in terms of u, and y is defined in terms of v. All right, so to go through and figure out, we got to figure out what all the branches represent. So if you have z and it's defined in terms of two things and you want to differentiate it, then you've got to use partial derivatives. And same thing, x is defined in terms of two things, so you've got to use partial derivatives. And same. Okay, and then this is where maybe things start to get a little bit weird, or the picture starts to get a little bit too complicated. But if you want to go from z all the way down to the bottom, see the bottom now has two variables. So this is the first one where we have the bottom has two variables. So if you're going to go through and actually take these two functions, plug them in here, we're still going to end up with partial derivatives for our final result. So the way that you can kind of represent that in your tree, if you want, is you could go through and do something like this from top all the way to bottom. We're going to have partial of z with respect to v, and from top all the way to bottom, we're going to have partial of z with respect to u. Okay, and so if we write out those individual definitions, we get partial of z with respect to u. What's that going to equal? To figure that out, we're going to multiply down the chain just for the u definitions, just for the u branches. So if you multiply down the chain, we get partial of z with respect to x times partial of x with respect to u plus partial of z with respect to y times partial of y with respect to u, and partial of z with respect to v, right? That would be this guy from top all the way to bottom, and then multiply down the chain. We're going to get, or down the tree, multiply, so we get partial of z with respect to x, partial of x with respect to v, plus partial of z with respect to y, times partial of y with respect to v. So we get two separate definitions, right? Which makes sense. If you have a function that's defined in terms of two things, you're going to have partial derivatives for those. And then each definition looks kind of like our last result, right? We've got separated with the with into two pieces, and then we're adding. Okay. So can we go through and show this is true in the same manner that we did the last one? You actually can. Again, it's not going to be showing it's true in general. What we're going to do is we're going to simplify these just to show it's true in just one case, a simple case. But it's nice to go through and do this because I like to do it because you see the justification for the plus. And so what we're going to do is we'll show that it's true if you could take uh, the outer function and we could separate it into two pieces. Or we could separate the x and y in the outer function. And then we're going to say that we could do the same thing for these two. You could say x equals L of u times m of v, and then y equals n of u times o of v. So we've got a lot of functions here, and so but that's the one case that you can easily go through and show, and so that's why we're going to do it that way. Now, so can we go through and get back to these originals? Well, so the way to do it is to take these two definitions and plug them in to actually create the composition. Right? So if we did that, we're going to have f, and then inside of f, we're going to have L of u times m of v. And then we have g, and then inside of g, we're going to have n of u times o of v. And so actually, this is the composition. This is the equivalent of the Calc 1 definition that we had all the way back at the beginning, where it's all written as a composition of functions. Now, how would we go through and differentiate this? So we could take the partial of, well, so, okay, again, now if you were to take, if you actually had functions here instead of just, we're generalizing this, like if this were cosine of u and this is natural log of v, right, then f is going to be defined in terms of u's and v's. And so because of that, when you go to differentiate, if f is defined in terms of u's and v's and g is defined in terms of u's and v's, then z is going to be defined in terms of u's and v's. So we have to do partial derivatives. And so if we just do the partial of z with respect to u, if you go through and calculate the derivative of this structure here, right, what you have is you have some u's and v's that are inside of another function. To go through and calculate the derivative of that, we're going to have to use the chain rule. Oh, hold on. Actually, sorry, we've got to take a step back. We have a function that's defined in terms of u's and v's and another function that has u's and v's in it. So if we go through and take the derivative with respect to u, we need to use the product rule. Sorry, I forgot about the product rule there. So you've got to go through and do the first times the derivative of the second. And so when we take the derivative of the second here, what we have is we have an outer function with some u's inside of it. Now, when we're differentiating with respect to u, we're treating v as a constant, so you can just pretend the v is not there. So what we have is we have an outer function and then some u's inside of it. That's our Calc 1 situation. So we can go through and just use our Calc 1 formula for calculating the derivative. All right, so we're going to go through and take the derivative of the outer function, and then we're going to multiply it by the derivative of the inner function. And when you differentiate the inner function here, you're differentiating with respect to u, so you're going to treat the v's like they're constants, and so you're going to end up with n prime of u times o of v. All right, the o of v, all whatever's inside that o of v, it's all treated as a constant, so it just drops down, and then to go figure out the derivative of n of u with respect to u is just going to be n prime of u. All right, and so since we're using the product rule, we've got first times the derivative of the second, and then we're going to have plus the second, which is g of n of u o of v times the derivative of the first, so you get n prime of L of u times m of v times the derivative of the inside. Now we're differentiating with respect to u, so we're going to have L prime of u times m of v. Okay, and now that we're finished differentiating, now if we go through and translate this back into our original setup here, we're going to have f, and where we have LUMV, that's x, so we're going to have x, and then we're going to have g prime, and we have inside of that NUOV, that's y, and then next to that, the derivative, we have n prime of u times o of v. Well, if you look at the definition for y, if you have take this and compare it to this, we just differentiated the u part. We left the v part alone. If you just differentiate the u part and leave the v part alone, that's a partial derivative. So we've got the partial of y with respect to u. Okay, and then there's that plus. And now we've got g of y times f prime of x. Yes. Okay. And then times L prime of u times m of v. If you compare these two, you just have differentiate x with respect to u. So it's the partial of x with respect to u. Okay. And then finally, the last step here, if you compare this with this, you could see they're the same, except I've differentiated the y part. So I've got the partial with respect to y. So it's partial of z with respect to y. That's this, right? So it's z is defined in terms of these two. So if you just differentiate the g, you've differentiated z with respect to y, and then leave this in. And then this is the derivative of z with respect to x times partial of x with respect to u. And that shows that the result that we got from our derivative tree, oops, sorry, not that's I pointed at the wrong one. The result that we got from the derivative tree did match up with the formula that we end up getting in this, again, special case scenario. It's not, this is significantly more complicated than this. I've said that you've got a function of x and y, but you can separate the x's and y's. You've got a function of u and v, but you can separate them. If you can separate them, then what I've done is I've proven that this formula is correct. But I have not proven that if you can't separate them, that it is. So you'd have more work to do if you wanted to prove that. Okay, and so those are a couple of chain rule results for multivariable functions where you've got a composition and you've got more than one variable, that's inside the composition. So that pretty much concludes my explanation for derivative trees and how you generate them, how they work. I went through and I showed that the results that we got do end up making sense in this in these specific subsets of the general case. So the last thing that I wanted to show you is, okay, how do you actually calculate a chain rule in multivariable then? If you don't use these definitions, if all of this stuff that we did is just for proofs, it's only for proofs, then how do you go through and calculate a derivative in multivariable with a chain rule? Well, what you do is you substitute, then differentiate. All right, so I'll show you. It's really surprisingly simple. Let's say we have z is equal to sine of xy. And then we have x equals 2t and y equals t plus 1. So in this case, could you go through and do zx, z is in terms of x and y, x is in terms of t, y is in terms of t. We got the whole tree, so the derivative of z with respect to t is going to equal partial of z with respect to x. Could you go through and do all of this? Could you create a tree? Could you create a definition? You absolutely could, and it would work. It would work. You could go through and do all of this work. You could just keep going, write this all out. You could go through and say, all right, this is going great. What's the partial of z with respect to x? You could figure that out, and you could just, slog your way through this long, protracted process to try and figure out what the derivative is. Or you could just substitute. Take the 2t, plug it in. Take the t plus 1, plug it in. Now z, define it all in terms of t. The derivative. Take the derivative, this is chain rule. Take the derivative of the outer function, cosine. Leave the inner function alone. Times the derivative of the inside. The derivative of the inside, you have product rule. First times the derivative of the second plus second times the derivative of the first. The end. You're done. So you can go through and calculate a multivariable chain rule derivative result in 30 seconds, or you could spend 5 minutes doing a chain rule definition and then differentiating all the separate parts, plugging everything in, simplifying it, back substituting. So long story short, no one calculates derivatives using the chain rule. Well, no one that I know anyway. I mean, maybe someone will respond to this video someday and say, that's how I do it. But I don't know anyone who actually calculates multivariable chain rule derivatives using derivative trees. Instead, you just substitute and then differentiate. Everything that we did in this video, everything is only for proofs. It will only show up for proofs in this class. I will regularly refer to the results of this video. We will regularly use derivative trees, but only when we're proving things. So the issue is that this scenario occurs, and we need to know in a general sense what the derivative is when we're proving something. So we need to know that this is the derivative. Okay, and so that formula is important, but it's just not important for actually going and doing calculations when you're actually doing problems. So I hope that that makes sense. Okay, so that concludes the video. Thank you for watching. See you next time.